Welcome to Math with Miss Garrity. Today we're going to talk about solving systems of equations. As a reminder, what is a system of equations? When we solve an equation, we're trying to find the unknown variable. What is the value of the unknown variable that makes this equation true? Well, when you have a system of equations, we have more than one equation and more than one variable. So this example that I just wrote is a system of equations. We are solving two equations that have the exact same variables. And what we're going to do is we're going to solve it at the same time. In other words, what is the ordered pair? What is the value of x combined with the value of y that makes both of these equations true? There are different ways to solve systems of equations. We could graph to find their point of intersection, or we can substitute. If one of the equations is solved for a single variable, we can substitute that expression into the other equation and then solve for the single variable. Or we can use elimination. Elimination is easiest when the equations are set up, lined up, actually like we have this situation where the like terms are in the same column. What we can do, I'm going to choose elimination for this specific example. When the coefficients of one variable, like the variable y, when the coefficients are opposite numbers, all you have to do to eliminate that variable is add the two equations. 2x plus x is 3x, 3x minus 3y is 0, 15 plus 3 is 18. We've eliminated the y variable, so now we just have one variable left, and we can solve for that, and the x coordinate is 6. But what is the y coordinate? Well, I'm going to have to go back to one of the original equations and substitute my new x value. So you can pick either one, because it's going to have to work in either equation. I'm going to pick this first one. So this first one says 2 times x plus 3y equals 15. 12 plus 3y equals 15. Subtract 12 from both sides to get the y alone. Divide by 3, and your y value is 1. So our goal was to solve this system of equations, and I think the solution is the ordered pair 6, 1. And what we can do is we can check with both equations. So if you substitute 6 in for x and 1 in for y, is this first sentence true? Is 2 times 6 plus 3 times 1 equal to 15? If it is, then that is the solution to the first equation. But now to solve the system, we need to make sure it works in the second equation as well. What's 6 minus 3 times 1? It's 3. So this ordered pair, when x is 6, y is 1, is the solution to our original system. Let's look at another example. Solving systems of equations. Let's look at the system that says 4x plus 8y is 3, and 8x plus 16y equals 6. Let's solve this system of equations. Well, Again, we could graph it, we could use substitution, or we can use elimination. Those are our options. Now, the system is lined up so that the variables, or like terms, I should say, are in columns, so that's good. But none of the coefficients are opposites. So what we can do is we can multiply one of these by a constant so that the coefficients are the same in both equations. So for example, what I can do is I could multiply this top equation by the constant -2. And I'm going to multiply both sides by -2 to keep the equation balanced. When I do that, I get -8x minus 16y minus 6 equals -6, -6. And then if I rewrite the bottom equation as it is, nothing's changed. Now I go ahead and add the two equations together because the -8 and the 8 are going to cancel. -8x plus 8x is 0. -16y plus 16y is 0. And then on the other side of the equation, I get -6 plus 6 equals 0. So here we have a situation where the variables were eliminated. Both variables were eliminated. So this leads me to know that this system has infinitely many solutions. Infinitely many solutions. What this true statement means is that there are an infinite number of ordered pairs of x and y that will make both of these equations true. And if we graphed this system, the graph would show us that these two equations are one line. Here, let's do another example. (3x plus 5y equals 27). 12x plus 20y equals 3. Let's solve this system of equations. We could multiply this bottom equation by 1/4 on both sides of the equal sign. And we would get 4x plus 5y, 3x, excuse me. We'd get 3x plus 5y equals 3/4. And then I could rewrite the top equation, 3x plus 5y equals 27. Now, at this point, I'm not going to add the equations because the coefficients are not opposites. So if I subtract the entire bottom equation, I would get 3x minus 3x is 0, 5y minus 5y is 0, and then I get 27 minus 3/4, so 26 and 1/4. This statement is not true. This tells us that there are no coordinates of x and y available that would make both original sentences true. So this we would write, there is no solution. There's no solution to this system. And if we graphed it, the lines would be parallel because there is no intersection. Let's solve another system. We're going to solve this system by substitution. And the reason I'm going to quick choose substitution is because both of the equations are set equal to the same variable. So if we wrote x squared plus 2y plus 1, that equals y. But that also y is x plus 4. So when equations are solved for the exact same variable, we can set those equations equal to each other. Now, solving with substitution, I've just created a single equation in one variable. So now I'm going to solve this equation. I notice that it's quadratic. So I'm going to subtract x and 4 from both sides of the equation, because in order to solve a quadratic equation, we need one side equal to 0. And now that we have both sides set equal to 0, I can solve using any of my quadratic skills. So actually what I'm going to do is I'm going to use the quadratic formula. X is the opposite of b plus or minus the square root of b squared minus 4 times a times c, all over 2a. X equals negative 1 plus or minus the square root of 13 divided by 2. Now, this is the x-coordinate that satisfies this equation, but we're solving a system. So I need a xy coordinate. I need to know the y value. Well, wait a minute. If we look at this number, the square root of 13 is irrational. So I'm going to go ahead and I'm going to round this to the nearest hundredth. I'm going to take negative 1 plus the square root of 13, and then I'm going to divide that by 2. One of my x values is 1.30. Now I'm going to take negative 1 minus the square root of 13 and divide that by 2. The other x-coordinate is negative 2.30. So when I go up here and I substitute my x values individually, I'm going to do them separately. I'm going to substitute it in for, I guess this would be easiest. So So when x is 1.3, the y value is 5.3. So there's one solution to the system. And when x is negative 2.3, the y would be 1.7. So I have two solutions to this system. And the system is nonlinear because both equations are not linear. So in a nonlinear system, we can have more than one solution. In this case, we have two. I'm going to check my work. I'm going to go up, I'm going to substitute it into this top equation because I used the bottom equation to find my values of y. So now I want to see if it works up here. So when x is 1.3, if I take 1.3 squared and add it to 2 times 1.3 and then add 1, will I get 5.3? And I do. I get 5.29. That's close because we had to estimate down here. So now the next one, I'm going to put negative 2.3, and I'm going to put it in parentheses because when I square a negative, I want to make sure I always put that value in parentheses. Let's see if the value of negative 2.3 works. Negative 2.3 squared plus 2 times negative 2.3 plus 1. 1.69, which rounds to 1.7. So we can solve systems of equations by graphing, by using substitution and by using elimination. And we can solve systems whether both of the equations are linear or nonlinear. And there you go.